Hello, and I am going to teach you electrostatics. In this chapter, we will study Coulomb's law, then electric field and potential. Further, we will study electric potential energy of the system. Then we will study electric field lines. Further, flux of the electric field. Then we will learn what the Gauss theorem says. Then we will come to capacitance, which will be taught to you by some other faculty. Coulomb's law. Coulomb's law states that the force between the two charges is equal to K Q1 Q2 upon R square, where R is the distance between the two charges, Q1 and Q2 are the magnitude of the two charges with the sign. K is equal to 1 upon 4 pi epsilon naught, and its value is equal to 9 into 10 to the power 9 with the proper units, which is Newton meter square by Coulomb square. Epsilon naught is the permittivity of the vacuum, whose value is equal to 8.85 into 10 to the power minus 12 with the units just reverse of that of K, that is Coulomb square per Newton meter square. The force in the figure, you can see that there are two charges Q1 and Q2. The force on the charge Q1 due to the force on the charge Q2 due to Q1 is denoted by F21, which is along the line joining the two charges. Vector form of the Coulomb's law. The force between the two charges in the vector form is given by F is equal to K Q1 Q2 upon R square into the R cap, which denotes the direction. The R cap, it is equal to R vector upon the magnitude of R. So this can be written as K Q1 Q2 upon R square into R vector upon the magnitude of R. This force is again along the line joining the two charges. For example, in the figure, you can see one charge is kept at the origin plus Q1 and the other charge at a distance of R from it. The force on the charge Q2 is denoted by F21 and is equal to the force which we have written earlier. Now the principle of superposition. It states that the force on any charge due to a number of other charges is the vector sum of the force due to the individual charges. The pictorial representation is as shown. So in this case, the net force F is given by Now we have a question for us. There are three charges Q1, Q2, Q3, all of whose magnitude is equal to Q. They are kept at the vertices of an equilateral triangle, and we have to find the force on a particle on a charge of Q0, which is kept at the centroid or the center of the triangle. So let's proceed with this question. Since the charges are of equal magnitude and at equal distance, the force due to all of them would be equal in magnitude. Now we have studied that the resultant of the two forces at an angle of 120 degree has the same magnitude as that of either of the vector. So the net resultant of the forces would be equal to F, and now we can say that the total force on Q0 is equal to 0. You can also proceed in another way. This is the numerical method of solving this question. The net resultant force upward would be 2F cos theta, as the F sin theta component will be cancelled. Now let us calculate the value of 2F cos theta. it is equal to F into and here the theta is 60 degree. So 2F cos 60 degree is equal to F, and again the net resultant force on the particle on the charge Q0 is equal to 0. So we can arrive at a result that for any regular polygon, if charges of equal magnitude they are kept at the vertices, then the net force on any charge kept at the center would be 0. Let us take an example to illustrate it. Suppose there are two charges which are kept at two of the vertices and no charge is kept at one of the vertices. Then we can substitute this. So now we can see that the force due to three of them would be 0, and we have to calculate the force only due to the left charge minus Q. So in this way we can make use of this statement. Now let us see an example. There is a charge Q0 which is kept at the center of a ring, and the total charge on the ring is capital Q, which is uniformly distributed. We can see that the force on the charge Q0 would be equal to 0, as the force due to each small particle on the ring would eventually sum out to be 0. Now we have to calculate the tension in the ring. For this we will take a small element. Equating the forces in the vertical direction, we get 2t sin d theta by 2 is equal to the electrostatic force, which is equal to K into dq into Q0 upon r square, where dq is the charge on the small element being taken. Since it is a small element, sin d theta by 2 can be written as d theta by 2. And further calculating, you can find out the value of t. Now we will see force dependency on the medium. Suppose a charge Q is kept in a medium which is not vacuum. So let us calculate the expression for the distance which will be valid in this case. So we find that the distance equivalent would be equal to R is equal to R0 into root ER, where ER is the relative permittivity. So far we have studied principle of superposition and the force dependency on the medium. Now let us do examples based on that. The first example is based on the principle on the forces which are kept at forces between the charges which are kept at equilibrium. So in this case we have two particles A and B of charges Q and 2Q which are kept at a separation D. A third charge particle has to be clamped between them such that A and B they remain at rest. Let us find the magnitude and the position of that charge. Suppose we have the charge 2Q kept at the starting, then the charge Q of whose magnitude and position we have to find, and finally the charge Q. Since A and B, they have to be at rest, so the charge on C, it must be negative. A is kept at rest, so the forces on A must be balanced. So force on A due to C should be equal to force on A due to B. That is, suppose A and C, they are kept at a distance x and the total distance between A and B is d. The force on A due to C is K minus Q 2Q upon x square, which should be equal to the force on A due to B, that is K Q 2Q upon d square. The second condition we have is that the force on B due to C should be equal to the force on B due to A. Since B is also at rest, so K Q into minus Q, the distance between B and C, that is d minus x, should be equal to the force on B due to A, that is K into Q into 2Q upon d square. So we have two equations and two unknowns, that is the capital charge Q and the value x, which we can find out by using these two equations. Now let us do a question based on force dependency on medium. We have derived the relation that R naught is equal to R into R naught is equal to R into root ER, where ER is the relative permittivity. So in this case, the force, it can be written as K, that is 9 into 10 to the power 9, Q1 1 coulomb, Q2 2 coulomb upon the distance, which will be, the total distance between them is 5 meter. So the distance in the vacuum is 3 meter plus the distance in the medium can be replaced by R root ER, which would be 2 into root 4. So in this way we can find the force if the particle, it is kept in a different medium or there is a medium in between. Electric field. The electric field is the force experienced by a unit positive charge. The charge Q, which is producing the source, is called the source charge, and which tests the effect of the source charge is called the test charge. So mathematically we can write it as electric field is equal to F upon Q naught. The direction of electric field and force F, they are same, and the unit of electric field is Newton per coulomb. Now we can see the direction of the electric field for a positive charge. For a positive charge, the direction of electric field is radially outwards, whereas it is inverse for a negative charge, the direction is radially inwards. Now suppose we have a charge Q. If the electric field, it is in the plus x direction and the charge is positive, then the force would be in the direction of it. However, if the charge is negative, then the force will be in the opposite direction. Now let us see the variation of electric field with x. In this we will take a few cases. The first case is when both the charges, they have the same sign. Let us analyze the electric field in the various regions. In this region, the electric field due to the charge 1 would be in plus x direction, as well as due to charge 2, it would be in the plus x direction. So the net electric field is in the plus x direction. In this region, the electric field due to Q1 would be in minus x, as well as due to Q2 would be in minus x. So the net electric field is in negative x direction. If we observe the electric field in the middle region, then we will find that there would be a point when the net electric field would be 0. as the electric field due to Q1 would be in minus x, whereas that due to Q2 would be in plus x. So we will have a graph like this. Now let us analyze the case when one of them is positive and the other is negative. Suppose we have plus Q and minus Q charge. In this region, the force the electric field due to minus Q charge would be in negative direction and that due to plus Q charge would be in positive direction. But the force due to the minus Q charge would be more as the distance is less, so the net force would be in the negative direction. Now let us consider this region. Here the force due to plus Q would be in the negative direction and due to minus Q would be in the positive direction. However, the force due to plus Q would be more as the distance is less, so the net charge would be in the negative x direction. In the middle region, we will have the charge due to plus Q in the plus x direction as well as due to minus Q in the plus x direction. So, the net electric field would be in the plus x direction. However, the force on the electric field just at the corners, it would be infinite as the distance r would tend to 0. So, we will have a minima in between. This corresponds to the minima which will be at the midpoint of these two regions. Now let us solve this question. Suppose we have two plates of length L and a charge is projected between them, halfway between them. The length of the plates is given to us as L and the electric field is supposed downwards. Since the charge Q is negative, the force would be in the opposite direction to that of the electric field. We have to find the angle of deviation as it comes out. So, let the angle of deviation be theta. So, tan theta, it could be written as Vy upon Vx. The Vx, it would remain u as there is no force in the horizontal direction. The Vy can be calculated by using V is equal to u plus at. Here initial velocity in y direction is 0. The acceleration is qE by m. And the time would be equal to L by u, that is the distance travelled in the horizontal direction upon the velocity. So, we can find that tan theta is equal to QEL upon mu square. We have not taken the acceleration due to gravity as it is written in the question that we have to neglect gravity. Now, let us consider the electric field due to linear charge distribution y. The first case we will consider is when the point is on the axis of y. Suppose the point is at a distance of r from a wire whose length is L and the charge density is lambda. So, the electric field, it would be given by k lambda L upon r into L plus r. You can find out the electric field, that is derive this formula by taking an element on the wire and integrating the electric field to find the net electric field. Now let us consider the case of a general point. Suppose we have a wire and there is a point which is making an angle of alpha with one end of the wire and an angle of beta with the other end of the wire. So the electric field here in the x direction, it would be equal to k lambda by r sin alpha plus sin beta. And the electric field in the y direction, it would be equal to minus k lambda by r cos alpha minus cos beta. Now let us consider some special cases. The first case is the case of infinite wire where the two angles would be equal to 90 degree. That is alpha is equal to beta is equal to 90 degree. Putting this in the formula, we will get that the net electric field, it is equal to 2k lambda by r. Then we have the case of semi-infinite wire. In this case, one of the angle is 0 degree and the other angle is 90 degree. So, we will find that the electric field at a point at a distance r is equal to k lambda by r in the x direction and k lambda by r in the negative y direction. Now the electric field due to ring. Suppose we have a ring with a charge q on it and a point at a distance of x. So the electric field would be equal to kqx upon under root a square plus x square whole to the power 3 by 2, where a is the radius of the ring. You can find it out by taking a small element on the ring and finding the electric field due to it. Similarly, we can take an element on the other side. We will observe that the net electric field would be along the axis of the ring. Now let us draw the graph for the electric field. From this graph we can see that the electric field will achieve a maximum value at a particular point. That point can be found out by differentiating the value of differentiating the formula of electric field with respect to x. We will get x is equal to plus minus a upon root 2, where a is the radius of the ring. Here y axis represents the electric field and the x axis represents the distance x. Now let us do this question where we have to find the time period. First of all, let us find out which type of motion it is. The force can be written as kqx upon a square plus x square whole to the power 3 by 2, as we have seen earlier. Since it is given x is much less than a, so the force turns out to be kqx upon a cube. We see that the force, it is proportional to x. Further, the direction of force is towards the equilibrium position, so we can say that the motion is SHM. We know the formula for the time period, which is equal to 2 pi under root m by k, where k is the constant relating f and x. In this case, this is the value of k. So putting this value of k, we can find out the time period for this. Now let us do another question in which we have to find out the electric field at the center C, where we are given that the charge density is lambda is equal to lambda naught cos theta. So we have to find the electric field at C. First of all, let us see the charge distribution on the ring. Since it is cos theta, it would be positive in the first and the fourth quadrant and negative in the second and the third quadrant. So we see that the electric field in this region would be in plus x and plus y direction, and in this region it would be in plus x and minus y direction. So the net electric field would be in the plus x direction. We can find it out by integrating dE cos theta. Now the value of dE, it can be given by k into dq upon r square into cos theta, and the value of dq would be lambda into r theta, where lambda is lambda naught cos theta. Integrating it from 0 to 2 pi, we can find out the value of electric field at C. Now let us do another question in which we have to find out the electric field at the center. Suppose we have a triangle made up of 3 wires, lambda, lambda and minus lambda, and the length of each side is equal to a. We have to find the electric field at the center. So here we will use the statement which I have told earlier. We can replace the charge minus lambda with lambda minus 2 lambda. So the force due to these 3 would be equal to 0, and hence we are left with a minus 2 lambda charge wire and the point. This angle is 60 degree. So we had the force 2k lambda by r sin theta, where theta is 60 degree. Lambda in this case is 2 lambda and r is this distance, which is equal to a upon 2 root 3. So we can find out the force in this way. Now let us see the electric field due to a circular arc. Suppose this angle is theta. Now if we take this element, then the electric field would be in this direction. And if we take an element here, then the electric field would be in this direction. So the net electric field would be along the angle bisector. And its magnitude would be equal to 2k lambda by r sin theta by 2, where r is the radius of this arc. Now let us find out the value of electric field at O. Due to this circular arc, the value of electric field would be equal to 2k lambda by r sin theta by 2, where theta is pi sin pi by 2 and it is equal to 1. So we have 2k lambda by r. Now due to this infinite wire, it would be k lambda by r and k lambda by r. And due to another semi-infinite wire, the earlier one was also semi-infinite, we will have k lambda by r and k lambda by r. So the net electric field at O, it would be equal to 0. Now we have to find the force of interaction between these wires. This is a semi-infinite wire. So let us take an element on the wire with charge density lambda 2 at a distance of x from the wire with charge density lambda 1. So the force on this small element can be written as 2k lambda 1 by r, 2k lambda 1 by x into lambda 2 dx. We can integrate this to find the net force from r to r plus L. Now let us consider electric field due to disk. Suppose we have a disk with the charge density sigma and a point at a distance of x from it. Now the electric field at this point is given by sigma upon 2 epsilon naught into 1 minus x upon under root r square plus x square, where r is the radius of the disk and sigma is the charge density. We can find out this electric field by taking a small element that would be a ring of width dr and then integrating it. So today we have studied the electric field due to wire, disk, ring, and we also studied the superposition principle, the force dependency on the medium. The most importantly, we studied the Coulomb's law, which is the basic of all what we are going to study further.